Okay, let us take off from where we left off for the midsem. So we had talked about the strain displacement relations, which is this is obviously symmetric. So this involves the use. Uh, there are three components of use, and then because this is symmetric with respect to I and j, so there are six components of epsilon. Similarly, we have talked about sigma ij. Again, we have shown that sigma ij is equal to sigma ji. This followed from the balance of angular momentum, and this means that sigma ij is also symmetric, and therefore there are six sigmas. So at any point x on a continuum, you have three displacements, six strains and six stresses. That means altogether 15 variables to be determined. Now, what do we have to determine these 15 variables? We obviously need 15 equations, and we had talked about the fact that these strain displacement relationships make up six equations, and then the balance of linear momentum told us that at every point on the continuum, sigma ij comma j plus bi has to be equal to 0. These are equilibrium equations, and then because I is a free index and j is a repeated index, you have three of them. So you have altogether 9 equations, 15 variables. Obviously, you need 6 more equations to square the story. Okay, now what we see here at this moment is that this strain displacement relationship, as I told you earlier, is a completely geometric relationship. It's a completely geometric relationship. It follows from geometry, and this is just an expression of geometry of deformation of a small cube drawn on the body. The symmetry of the stress tensor is an outcome of a physical law, a general physical law, the law of balance of angular momentum, whereas this equation is an outcome of another physical law, the law of balance of linear momentum. So all of these are kind of sacrosanct equations. The geometry, obviously, with the assumption that the displacements and their gradients are small. With that assumption, the geometry is sacrosanct. This follows from a physical principle, therefore sacrosanct. This also is following from a physical principle and therefore sacrosanct. And these are equations that do not talk about the material at all. These would be valid for any kind of material as long as the assumption of small deformation is valid. So these equations are sort of what I would call God-given equations. So you have 9 God-given equations, and you need 6 more because you have 15 variables at each and every point. Now these 6 additional equations are going to come from what is known as a constitutive relation. So a constitutive equation would give you another 6 equations. So constitutive equations are of the form sigma ij equal to, or so constitutive equations connect the second order stress sigma with some function which is a tensor function of a tensor variable, that is epsilon. So it is a function that connects stresses to strains. Obviously, this function can depend on strain only, but it can also depend on other things. For example, it can depend on the temperature, it can depend on the density, and so on. And sometimes it does also depend on strain rate. So this kind of a relation, which connects stresses to lot of external variables, including the strain, is called a constitutive equation. And as you can see, that this obviously gives you 6 equations in the 6 components of stress, which means now we have 9 plus 6, that is 15 equations for the 15 variables that we have to solve for. So these 6 equations depend on the material that we have, that we are considering, and these 6 equations are man-made equations because these 6 equations are not derived from a physical principle, but would be the outcome of experimental testing. So you test a material, you figure out what its stress strain relationship is, and then uh, frame these 6 equations. Now, in our case, at least in this course, we are going to take a rather simple stress strain relation. So we are going to forget about all these dependencies and just have a stress strain relation which depends on strain. So if I know the strain, then I know the stress. This kind of a material is called a hyperelastic material for reasons that I will explain a little later. But this is a stress strain relation that we are going to use in this course, that the stress depends on nothing other than just the strain. Not only that, we will assume that the stress depends linearly on the strain, which means that every component of stress, sigma ij, is dependent on every other component of strain, which means we can write this as something like this, where KL is a repeater index, and when you write it out, you will see that every component of strain will appear on the right hand side. Every component of strain will appear on the right hand side, and these are constants. These are constants which have to be determined experimentally, and will give you the constitutive equation for sigma ij. Similarly, for every six ij pairs, you will have 6 such equations, and therefore you will need altogether 81 constants, to specify this completely. Now this is known as generalized Hooke's law, and is a standard constitutive equation that is used for many materials which are in the linear elastic regime, which undergo reversible deformation, which means that if you reduce the strain to 0, your stresses come down to 0. So it's a reversible deformation. Also, if you linearly increase the strain, the stress goes up linearly. If you linearly decrease the strain, the stress comes down along the same path. So there is no hysteresis. There is no dependence on history in the material. So the material does not remember what you have done to it earlier. There is nothing in this constitutive equation to tell you what you have done to the material earlier. So this is history independent. This is the simplest kind of constitutive equation that you have, but it turns out that it's quite useful. This kind of a constitutive equation is quite useful for a large range of materials which are in the small strain regime. When you deform materials by small strains, many materials actually obey this kind of a linear generalized Hooke's law. So this is where we will start from. Let me stop this video here, and we will start with a new video explaining how we deal with these 81 constants. Do we have to determine all of them experimentally, or can we use some other considerations to reduce the number of experiments that we will need in order to determine these constants?